Yeah, I will start. If anybody join later, so be it. If not, we will do this anyway. So it's the presentation for the bus protection. If anybody got Elliot is here. Okay, so yeah, it's the smallest group actually I had in months. Actually, first time that we are under 10 people. It doesn't really matter. I will go forward. The webinar is recorded and will be posted on the PMC website under my page with the webinars and tools for different helping tools for HRE and MATbase and stuff like that, standards for transmission lines. Again, if you have any questions, please do not hesitate to ask or interrupt me. That is, something that I enjoy to explain better if I didn't do it first time. Bus protection. So here are bus configurations. The most important bus configurations, when we say bus, is the high voltage and medium voltage, single bus, main and transfer bus, double breaker and single breaker, breaker and a half, very popular on the distribution, and the ring bus. The ring bus is what we have in the switchyard for high power and utilities connected to the transmission line. Almost always is the ring bus. For a lower power substation switchyard, sometimes we have the double bus, double breaker. And for the distribution, as I said, either is a very simple one with a single bus for a small application. Medium voltage distribution typically is breaker and a half. The reason is because of it's giving you a lot of flexibility and you can transfer the loads and so on. So the bus looks like the line on the top. That's the bus. It actually is a copper or aluminium, typically aluminium with a round or rectangular cross section. For those rectangulars in the middle are the actual breakers, and then on each side of the breaker we have current transformers. Now what you see with dash line is the zoning. So one zone encompasses and overlaps. You see is going up to the CTs, the current transformer on the feeder down there, and the others are starting from the upstream CT. The reason is that you can only measure what the CT is seeing. So if a fault is happening, let's say the CT is at a distance from the actual bus, if right there on the bus happens something, the CT will not see it. But as we apply the 87, the totalizer, that doesn't really matter because we will have a summation of the currents based on the Kirchhoff law. So the sum of the currents must be zero. Sectionalized, some improvements here. So for the purpose of not taking in out of service the whole bus when you do maintenance, you can have a little bit of improvement here with a breaker that is positioned right at the half of the bus, and then you have CTs both sides of the breaker, which is typically the arrangement. Now for saving money, as everybody does today, you may have a second solution that is B in these pictures with CT on one side. Now the zones, you see the zone is changing. So the selection of the zone protected is basically dependent on the CT position. So where is the sensor that will tell me that we have a problem, we have an overcurrent. So at first one is overlapping, you see is going to the CT across the breaker the other side, from the left to right or from the right to left. and the actual interconnecting the two buses, the sectionalized bus breaker is overlapping. The overlapping usually happens like 20% of the bus. Single sectionalized bus, switch with switch. So this time we don't have a breaker, we have a switch in between. In this case, basically we don't sense the current because the switch cannot operate under load condition or short circuit. There are load switches, but not for short circuit. It cannot open under short, so there is no point to measure across that because we will not order this switch to open. We will confer protection to this bus by disconnecting all the breakers, the loads, in case of a fault. So now we have two zones or one zone. So what this is showing you that the configuration of the zoning in the relay protection must follow the actual dynamics of the bus. So if the bus is closed, so you have one continuous bus, there is only one zone. And then yes, you have the feeder zoning, and that doesn't change. But if the switch is open, the zone 1 and zone 2 are encompassing each one half of the bus. Any questions up to now? Any questions is a good question. Main and transfer bus. So in this case we have the main bus on the top and then a transfer bus on the bottom. So what's happening here is each feeder has a breaker with CTs on both sides, and then you have a switch on the top and the bottom in continuation for maintenance and isolation purposes. And then you got another switch that is connecting to the transfer bus. So how this works, when we energize the actual breaker from the bus and we want to do the transfer, we will close the switch to the transfer bus that must be synchronized with the main bus, and it should be smooth and bumpless, and then we disconnect the breaker. So this will be make before break transfer from the bus, main bus, to the transfer bus. As such, when you open the breaker, the power already is connected to the transfer bus for that leg. So this is another configuration, breaker substitution. This is kind of an economic version of the double bus double breaker. So you only have one breaker on the right hand side, the TB, the transfer breaker, and then you have the main bus on the top and the transfer bus on the bottom. So this time this transfer breaker is the one that will supply from the main bus to the transfer bus. And what this is showing you is the transfer when it's happening from the breaker that you substitute. You open the breaker, you see on the left hand side of the TB we have a breaker that is open and the switches are open. So we want to take that out of service. How do we do that? Well, we're gonna close the TB breaker and we're gonna close the switch on the transfer bus for that load, for that feeder. And then we're gonna open the breaker, and last one we will open the switches upstream and downstream of the breaker. So always the switches are after the breaker, or if we connect a breaker with switches, the switches are before the breaker. The switches cannot handle the inrush currents and the stress, mechanical stress, as a breaker does. So the configuration of the zoning is changing. So you can see that by doing this modification in the operation of the bus, you change the zoning from the previous one. Now the breaker that is in substitution for repair does not take part because there's no current there, but instead is replaced with the TB. So the transfer breaker now is part of the zone and is replacing the original breaker that is now out of service. Is a dynamic change. That's why in the new relays you can do that very easily. You have logic in the new relays that can consider these transfers, so you know when the breaker is out of service, and you can even have different settings, as we're gonna see. 4 different configurations. It's called dynamic settings. Double bus, double breaker. This is for higher power. Basically is twice the single bus, single breaker. The feeders are in the middle, and then you have a zone 1 for the top and a zone 2 for the bottom, and another zone that encompasses for each feeder the breakers and the load. Okay, so this is double the expense, but is a very robust system. If you have a fault on any of the breakers, the other breaker can actually supply the power equally. So 2 identical buses with identical breaker, north and south, they can supply power on each feeder. Double bus with single breaker. So this is the same idea. You have double bus. The bus R size for the full load is not just a transfer bus for a single load. You can handle the full load on both buses, but you only have a transfer breaker. So the same idea, the transfer breaker will be closed when you take one of the breaker out of service. Now the zoning is zone 1 encompass everything up to the CTs after the breaker, and the feeder for each one is from the upstream of the breaker, so they overlap. The idea is that we don't want to leave any part of the bus outside the protection, so any little piece of the bus unprotected is a problem. So we prefer to have overlapping, like you see in this picture. Double bus single breaker with bypass switches is similar to the previous one, but if you observe here, each feeder has a bypass switch. So basically I can close that switch after I close the breaker on the feeder, and then I can take off the breaker and the additional switches, so to isolate the breaker for maintenance. Has a bypass switch that previous scheme did not. But as far as the zoning is identical with the previous scheme. That's how the protection will act, zone 1 and zone 2. Breaker and a half. There are simplified solution to breaker and a half. Doesn't need to be exactly with this structure. This is the most complicated one, to say so. You can have, you see one of the leg that go from bus 1 to bus 2. In power we call that diagonal, even though it's not a diagonal of a circle. You hear that in our substation, in our switchyard also, people talking about diagonal breaker and so on. It's just the breaker that makes a link between one bus and another. So in a simplified model, you may not have the middle breaker. Here you have 3 breakers. You may only have 2, and if you have just 2 feeders, basically you have 2 breakers and the feeder. So a lot of the distribution substations are like that in Darlington. The 44 kilovolts distribution is almost everything is with a breaker and a half, a simplified version. This one, how you transfer the load? Well, easily, if you have a breaker fault on tripping on bus 1, you will have the bus 2 connecting to that load. If the load is problematic, then it will trip again and you will have to deal with the outage for that feeder. But is a duplicated kind of similar to the double bus double breaker, but the middle breaker, the tie breaker, is shared between the bus 1 and bus 2. Hence the name of breaker and a half, because you don't have twice the middle breaker, and is shared as a functionality between the 2 buses. So breaker and a half has a lot of flexibility and is more cost effective. For lower power and medium voltage is the preferred solution. If you don't want to go on a very cheap solution, that is the single bus single breaker, but that is for very isolated small applications. The zoning, you can see here zone 1 and zone 2 are for bus 1 and bus 2, and then you have a zone 3, I will call it, that is for the actual feeders, including the middle tiebreaker. The tiebreaker normally is open, so you will have bus 1 feeding the feeders upstream and bus 2 feeding the feeders downstream. However, they all size 100% power, so you can actually feed all the loads from one bus or the other via the tiebreaker that is in the middle, and that is not normally closed. Only for special applications like hospitals and something that can not interrupt power, then that breaker may stay closed. So what's happening if we close the breaker? Well, all the short circuit power that goes to the feeders is double, right? So because we feed now from 2 buses, we will have double the short circuit available power, so you will need to size that feeder for that event, you know, the kiloamps that you have there. So that's the disadvantage to have a permanent close. Now, for the moment, we transfer from one to the other, even if it's a switchgear that is doing a make before break, the time is so short that we will not size the feeder for the double short circuit. We will neglect that little transfer, and for the time being, we will have the same sizing, either is on 1 or 2, the permanent steady state. Ring bus is what we have in the switchyard. So the switchyard is related to this. Ring bus means each feeder get connected to 2 power supplies at the same time, so it can receive power from left and right. And if one breaker trip, you interrupt the ring, but the power continue to flow through the other breaker. It's a very robust system, and this is the standard switchyard configuration for all the major utilities. You cannot use directional protections here because you don't know how the current will flow from left or right, or if it's open or closed. So the directional protection, like directional power 32 or 67, is not possible to be used here. Type of bus protections. So what we up to now, we went quickly over the bus configurations, and now to see what the protections are for these buses. So we will have differential, zone interlocking schemes, time coordinated relays overlap the bus zones, fault bus, and specialized sensors like in the gas insulated switchgears SF6. Influence factors for the protection design: the bus arrangement, definitely. If it's flexibility and you have different configuration, you need to consider all the configurations when you select your protections. You need to analyze all the situations. Availability of the CTs. If it's a new design, you need to make sure that you place the current transformers in the right spot to cover the complete bus, as we said, and overlapping the zones. For the refurbishment, we have what we have, the CTs. We can ask for additional CTs maybe to improve the protection, but typically is what is there. Reconfigurable buses available. Yeah, so if it's a switching bus, you may have dynamic settings for tripping on higher currents. Let's say when you parallel and you work with that for a while in with 2 sources or the zones, the tripping. All depends where you actually have the breakers, because don't forget there are only 2 things that can cut the short circuit power. Either is a circuit breaker or a fuse, or combination of this. There is nothing else can be used for cutting a fault on the bus. Performance requirements: security, selectivity, speed, sensitivity, cost, and complexity. Those are factors that you will need in the project to consider. Zones of protections. So here we have some examples of blind spots. I will go to that previous slide is explanation for this one. So what we see here, we have a blind spot for the network. The network is on the right where we connect the load. So basically you see the CT, both CTs are on the right hand side of the breaker. So everything that is on the left hand side to the breaker is not going to be sensed by the fault that is happening on the load side. But all means, if you have a tripping spot, over tripping spot is for the bus, because the bus will see that with other sensors that are on the bus and will trip, but it need to overreach over the breaker. So that is called over tripping spot, and for the network or load side is a blind spot considered. If you move the transformers on the other side, both of them, then now we have a reverse situation. So we have a blind spot for the bus. So the bus will not sense that current because it's ending short before the breaker, but we have an over tripping spot for the network or load. The load will see that short even though it's not on the load side of the breaker, because we position the CTs wrongfully. Normally these CTs should be positioned one on each side of the breaker. This is the correct side positioning of the CTs, up and down or left and right on each side. And this time we still have another problem here. In this situation we covered properly the bus and the network or the load, minus this stub. So if this is not a continuous bus to the load and you have a switch, basically that little portion from the bus to the switch is called the stub, and that is another zone. So we will see dedicated protection for that only, or need to be included somehow in the protection that you have from these CTs with a special arrangement. And this slide will consider the switching. So this side is mostly to show you the reconfigurable buses. So if you have two buses that feed the load, bus 1 and bus 2, then the zoning should change. You have a zone for the feeder that is always from the top CT to the load, but then when you close one switch, that switch will become part of the zone, and if you close bus 2, that bus 2 switch should become part of the tripping boundaries, right? So it's commented on the bottom, bus 1 zone tripping boundary, bus 1 zone measuring. So in this case the zone 1 is dynamic and is changing with the switch closing 1 or 2, and this should be reflected in the relay logic. Different protection, differential connection, overcurrent, instantaneous and time delay, percentage differential, high impedance differential, partial differential, and fault bus. So here we got differential connection, overcurrent scheme. Simply what we see here, the overcurrent is connected to all the CTs. As long as this circuit doesn't have leakage current to the ground, then we have a balanced summation of the 3 currents or 4 currents will be, in this case, 0. So all overcurrent will not trip. However, if this summation is different than 0 because of the leakage current, then the overcurrent will have a trip, and usually is through a time delay, similar to 5051, and even can be implemented with 5051, but we still in this configuration claim that we have a 87, because we are not looking at strictly one CT, we are looking at the summation of the CTs. Differential connected overcurrent scheme, same idea. We have the actual CTs summation, and this time we are not connecting the cities to the ground. So here you see the cities are going in the overcurrent relay on one leg. The other leg of the city is going to the ground. And the overcurrent relay is also connected to the ground. That's why we need to be very careful how we connect the relay. So the circuit of the CTEs are closing through the grounding system. Either the next scheme, the difference is that we don't connect to the ground. In this case, we have one leg of the CTEs connected together, the polarized one with the dot. They go on left hand side, and then all the others are connected together on the right hand side. We're using some stabilizing impedances. This is mostly for the electromechanical relay. In the new digital relay we don't need that. It will be taking care of the stability on the digital relay by internal resistance. But this is an electromechanical example. So now we implement the 87, as you see, with a 50. Basically is a instantaneous strip on the difference between the two legs of the CT's current. And as an example, you may have a fault on the first one on the left hand side. So what you can see here is also the direction of the currents, that on the left first feeder the fault will be, we will feed the fault from the bus, and the other feeders will change the direction of current because they all gonna go into the fault. That's why if we use feeder protection combined with this, we will block from tripping those other three feeders by using for instance a 67 relay. 67 is a directional overcurrent relay, and we will set up the relay to trip only for going the current from the bus to the load. And any reverse power like this one, we may not want to trip. We may want to trip the breaker on the left and then leave the other three feeders alive. Is a better protection. But this example is how you implement the 87, and you can see the direction change from one to the other. Now I want to mention something else. All these protections, we say current change direction and this and that, but basically it's not only the current, it's the shape of the current change. Yes, it's changing direction with 180 degrees on the other feeders, but that current will be dominant in a zero sequence and reverse sequence. Will not have a direct sequence only. Will be a very severe change. That's why the sine wave is not there. The current is not a sine wave anymore, because the zero sequence and reverse sequence, adding it to the direct sequence will make it look very distortioned. So the current will not be a sine wave. And yes, the CT may be saturating, so we'll need to consider that. That's why against the saturation we have those impedances that limit the reading of the current in the relay, protects the relay as well. So CT saturation is unavoidable unless you are using the new Hall effect current transformers that are based on electrical field, and you got measurement of the electrical field and amplified in current with beta A 3900 39,000. That is a different story, but need plus minus 12 volts. Any other CT is a protection CT, is not an instrumentation CT. There is a lot of confusion out there. We don't use instrumentation CT for protection. This CT is not saturating easily. It is a large magnetic core, but it has a time delay to saturate. Eventually does saturate, but is guaranteed to maintain the error, let's say 5% at 10 times rated current. So that's translated in the standard as a 5P10. So the CT will accept, you know, 5% plus minus. The error is not a problem for the protection, because the protection doesn't need to be, you know, very precise. Is a range where we want to trip. in order to protect the system and avoid the damage curve. High impedance differential. So this time we deal with high impedance of the grounding system, and we need to be very sensitive to any variation of the current. So typically it's considered high impedance anything that is above 1000 to 2000 ohm. Low impedance will be in the range of 10 or less. So for this one, the high impedance characteristic is a straight line. We're going to see it in one of the graphs. And the implementation is shown in this slide. So we will have again the CTs connected like this, not to the ground, and then the IR here is the actual relay current, the VR is the voltage across the relay, and we will need to protect the relay coil via MOV, metal oxide varistor, that anytime the voltage goes beyond the limit, this MOV will just open and protect from over voltages on the relay coil in this case. So that's the typical arrangement for high impedance grounding. High impedance differential. And here you can see the currents I was talking about. So this is the current, you see the three-phase current, and then you have the total current, the MOV when it's actually conducting, and the relay current you see is totally non-sinusoidal, and then the voltage is the last one, which shows you a lot of harmonics if you want, but really we talk about in protections not that much of harmonics. Harmonics 3I0 is what interests us, and those are multiple of 3, and yes, they are composed by harmonic 3 and multiple of 3, like 6, 9 and so on, but really those are the one that change direction as we showed, and they are the one that cause trouble between the neutral and ground, let's say, of a transformer. It can even burn out the neutral to ground link if it's not protected properly, even though you have a cross section equal with the phase. It happened. High impedance differential operation internal fault. So for internal faults to the system on the bus, this is the same. It's showing the direction of the voltage and current, similar to the previous one. The previous one was a fault on the feeder, and now we have a fault on the internal system, that is the actual bus, and the currents in this case look even more distorted. So you can see here the third harmonic more than you saw on the previous one. The idea is that the high impedance ground should not disturb the differential. The differential should trip for internal faults only, should not trip for external faults. But it's very hard to achieve that with the high impedance ground. The percentage differential is easier because you can instate slopes. We will see the graph, and I will explain how you avoid the differential for tripping on outside the system fault. 87 is for a system fault internally between the two CTs that read the input and output of that current. High impedance with MOV. Here, as we said, this is the 50 that trip for the 87, and 59 is just an over voltage protection, and then we have the MOV protecting, and the 86 lockout relay close for the protection of the actual relay. So that's the protection mostly on the right hand side, and then the 50 is the actual trip whenever we have a fault like the feeder fault. Operating current, this is calculation of the operating current, and we will not insist on the formulas. And differential, so is restrained and the operation current. One is the summation pretty much of the current, and one is the difference between the currents, and the graph is between the two. Differential with percentage restraint, so this is the most typical one that we have in the plant, the differential protection percentage, This is reading the current from each feeder into the relay. You see RR, those are restraint coil, and then O is the operating coil. Restraint coil is opposing the trip until the operating coil torque is larger than the restraint coils. So you can think about an electromagnetic disc that has a spring, and once the spring is not strong enough, the currents will induce voltage current, and the torque will be higher, so it will close the contact and will trip. That's why you have settings. You adjust actually the spring, how strong it is. Typical percentage restraint. So these are the characteristics for the percentage restraint, and we got this operating current on the graph here, and then the horizontal on the vertical. On the horizontal is the restraint current. You see, starting from a certain different than 0 point, because you want to avoid the trip because of the mismatch of the CTs. So the CTs may have a reading difference, and you don't want to trip on the error. And then is a slope that is selected based on the impedance of the system and the available short circuit power of the system. In order to avoid the 87 from tripping on external fault that is not between the CTs in and out, you introduce slope, and it may introduce more than one slope that also take in consideration the saturation of the CTs. And you have different characteristics here with slope 1 and slope 2. It's very typical to have more than one slope setting. You have an error and then the two slopes. And another example for a digital relay is actually an adaptive slope that you can see on the bottom, with the operating point above the line and restraint where it's not going to operate under. So under, it may be a fault outside the 87, but it's not going to trip the 87. So the system knows that some other stuff happened in the vicinity of the equipment and the device. Typical events on a percentage differential. So here is how it's moving the point during a fault, during saturation of the CT, and during a fault inside the system. Light internal fault is moving, you know, at the bottom left, and then you have a strong internal fault on the right. Okay, so these are example of moving operation points on this graph based on the events. And again, operating current is the difference in minus out, and then the restraint typically is an average summation of the CTs. So is sum in absolute value, not vectorial, summation of those currents over the number of feeders or input or CTs. Unrestrained operation. So in this case you see a straight line as opposed to the slope, the bottom one. You have a straight line and a high set, so everything will be operating only above the straight line, and this is the characteristic for an unrestrained operation. For high impedance grounding, typically. Trajectory of internal and external. So internal fault will trip, is above the line. External fault CT, saturation in progress, if it's severe, it should not trip. Initially is not tripping, but if it's severe and saturate in progress, it may get to trip point, which is not what we want. External fault with CT saturation. So here is the actual waves, how they look. External CT fault and internal, and the vectorial summation, and the current is in pulses. Here is digitized. Differential protection with linear couplers. So instead of using CTs, we are using linear coupler, is Hall effect really. And then you have a 59 that is looking at the over voltage across this, as opposed to look at the current, is looking at the voltage in this case, and the voltage will increase as the current unbalance between the feeders is increasing. Those are used in SF6 mostly. Rogowski coil is another subtype of the Hall effect, with 59 again over voltage on the left, or you have a percentage restrained on the right, also with Rogowski coil. Not so popular, but they are available. Zone interlocking is when you actually detect the fault in a spot, and through a network you control the protection upstream, and you order that protection to trip or not to trip. And the communication should be from the relay to relay. The smart relay do have communication. You can have pilot elements, fiber optic communication, and usually is IEEE 68180 is the Goose protocol mostly used, but can be DNP3, DNP4. So what's happening in a fault, the actual upstream feeder, even is seeing the fault, is blocked by the downstream feeders. Any of those relays can block the upstream to avoid total tripping of the bus. And this is via network, secure qualified network, and is faster than the coordination that we will normally do in a classic TCC curves, time current curves. We can do that, but pilot protection, as is called this one, for a larger system works better, especially if you have large bus bars and large distances between the relays. Directional blocking scheme. So now is 67 present and is only gonna trip for a certain direction of the fault, as we explained already. And then you have the link breaker, the TB, and the forward current that should go in one direction. In case of a fault, the bus blocking scheme, dual source sectionalized bus, so we'll only trip for a certain direction of the short circuit current. Fault bus relay scheme. In this case, we are looking at the bus fault via ground insulated terminal cables shielded to prevent relay for cable faults. So fault bus relay with a 50 relay on the right on the fault. So what's happening here, we are reading directly the current that is between the neutral of the system and the ground. So this one is mostly the direct current flowing from the neutral of the system into the ground, and that includes the shielding. And be careful, the shielding must be rated for that current. Partial differential is when we don't have enough CTs and we work with what we have, so we may not protect the whole bus. We have the load here, and then the overload on the top protection, but we only have the CTs on the bottom. So we have a 51 protecting the feeders, and the other zone is the load with the overload only. So partial is called partial differential, because on the top we don't have a CT for the protection, is a different type, is for overload. By the way, we need to match the CTs very much so, and if possible the same ratio, the same class of precision, to avoid spurious trips and errors that can occur. We need to match them as good as we can. This is differential with impedance relay. So we got a 21 relay, is also called impedance relay. So what this one does, need to receive the voltage. You see you have a potential transformer, and the CTs is looking at the impedance on the bus. So this is used for large buses and transmission lines, typically as primary protection for the transmission lines, secondary protection for generation and utilities. Even on, we have 21 even on the standby generators and EPGs. We could have had on the main generator. Somehow it was decided to put a 51V, which is looking at the overcurrent function of voltage drop when the generator trip, because a small current can still represent a short circuit on a lower voltage when the generator is tripped. But 21 traditionally is used for reading the impedance of the line on a certain direction. Is called the torque direction. The impedance of the line, as far as no fault is there, is of a certain value. So you have a circle of this characteristic that is real by imaginary, resistance, reactance, and once that impedance is lower because of the fault somewhere on the line, that point of operation goes inside the circle, and that's the moment this 21 relay will actually trip, whenever the actual impedance is lower than the normal value. So that's distance relay in a nutshell. MHO relay, you can call it. There are other subtypes, but this is a MHO because homopolar is what is using the impedance. Combined bus and transformer protection, very typical 87T for transformer. What you're gonna have as an input is the two feeders on the right, and then the transformer primary on the left. They have a total of 0 as long as there is no fault, and once the fault appears, this is different than 0. So this is a very typical 87 for a transformer. And yes, you can include the bus sections, the portion of the bus that is feeding the or is connected to the transformer. So you can have that included into the 87T. Implementation typically can be with Schweitzer 487E, can be also GE T60 transformer protection, which we have in our Unit 6 and Unit 3. Bus protection with grounding transformer attached to the bus. Whenever you have a grounding transformer, you put that in for two reasons. Is usually a zigzag transformer, and what it does is collecting the harmonics, so represent a 0 impedance for the 3I0 going to ground normally, and a high impedance for the 60 Hertz. So it's a very efficient method to clean up the harmonics on the system, or unbalance harmonics from the unbalanced load. But when a fault happens, right here in example in the middle feeder, this will create the 3I0 to move 180 degrees and will go upstream to feed the fault. So for this one, simply we will sense the direction of the 3I0 compared to the direction of the main current in the other feeders, and change it 180 degrees, and even in amplitude will trigger the relay to trip. So that's 87 with a grounding transformer. Why you have grounding transformer also is for creating artificial neutrals. So if the system is a three-phase, but you need a neutral that feed loads that is one phase, you will need to have a neutral, and that neutral is possibly created with a zigzag transformer. So that's when you're going to use this transformer relay applied to the bus protection. So this is 87 with summation. Instead of reading the actual current to ground, as we did, remember the neutral to ground current directly, if it's not available, you can read the current on each phase, on each feeder, and do the summation. The summation of this is REF, typically is marked like restricted 64 REF, and that is the ground fault detection via zero component. So the summation of the currents is done in the relay. In the past, the electromechanical relay will not have that possibility, so we will have a current transformer that does the summation of the other CTs and will go into the relay to trip. That output will be the vectorial summation of all currents from the feeders. New relays, they don't need a summation CT, and they do the summation inside the digital relay. Okay, so that's not so precise, it's not the preferred method, but sometimes you don't have a choice, you don't have access to the neutral to ground, or there is no CT. Connection when using scheme with differential ratio. So if you have different ratio of the CTs, that was a major problem in the electromechanical relays. To compensate for that, to do the scaling taps. In the new relays, that is absolutely no problem, because you will set up the inputs to the 87 and 87 function in a digital relay. It will know, because you put the right setting, what is the ratio and what is expected as an output as normal secondary current. Parallel current transformers. This is for restrain low impedance, bus protection, CTs going to the 87 percentage differential, and here is an example of current circulation between two CTs, and it's not measuring the external fault that may be between the two phase, because you see the fault is on phase 2, on feeder 2, because of the settings as explained on the slope. Remember the slope 1, slope 2, that is there exactly for this, to disregard faults that are outside the zone. If the zone is included, then you want that to trip on the fault. Dynamic bus. Now 87 traditionally came from the bus protection, but it extended, as you already saw, the transformer protection has 87, and there are two types. Is the one that we saw for the comparing the phase with the neutral to ground, and then is 87 across primary to secondary. So there are two types of 87, and they are used only for larger transformers, larger than 20 megawatts. Then you have 87 for motors and generators. They have exactly the same idea as a transformer. Don't forget, a transformer is just a particular case of a motor, induction motor that doesn't move the secondary. So all the protections pretty much from this point of view, 87 can be related to a large medium voltage motor or a medium voltage generator, large generator as our main generator, or EPGs and SGs. Bus replica, double bus, single breaker. So here we got the transfer through the CB4, right? So this is when you have a dynamic change and the zone change, and you can take care of that with different settings for different zones to incorporate that in your logic and change even the settings based on the switching of the power. Example of this zoning change is here. So we got a zone that is the blue zone for after the transfer to the transfer breaker, right? So now we need to incorporate the transfer breaker as opposed to the normal breaker only, because we have closed that breaker. So transfer breaker need to go in zone 1 and also in zone 2, because we operate that to transfer from loads from bus 1 to 2, so during transfer. Bus side CT considerations. Yeah, we kind of talked about this. What is happening if you have a fault when you don't have the CT, you will not know. So this is the lesson learned here. You need a CT on both sides of the breaker. Yeah, there is a time delay to open and close. How do we discover a breaker fault? Probably is a slide after this. Breaker fault will be identified via either auxiliary contacts that are not operating synchronized with the main power contacts, 52 or 33. 52 is the power, 33 is the auxiliary, so 52 and 33A need to be in sync. So whenever the breaker close 52, the 33A close, the 33B open. If that doesn't happen, is an alarm for the breaker fault, because it looks like something is wrong with the breaker. The other way to read the breaker health is via currents. That's why is another reason that we have the CT on both sides of the breaker. If you claim that the breaker is closed on all three phases, you should read the current on all three phases on both sides. If one side doesn't read that, then you have a problem. Now there is a time delay here, and the time delay to open or to close is because the breaker needs a time to open or close. So we will not trip instantaneously on this breaker fault which read the current across from one side to the other side of the breaker. Later we will have a time delay. Now on the closing, that time delay is very short, is a quarter of a cycle, because we have by standard, IEEE standard for breakers. By the way, these slides are from IEEE C37.234. So this is the IEEE standard where I extracted this. If you want to read the whole standard, it will be uploaded in the same spot on the website, PMC website. So there is a limit for the non-synchronization between the phase A, B, and C. They need to close with a maximum time delay between the fastest and the slowest between the three. Otherwise it's considered a fault. You cannot have phase 1 and 2 close and 3 after 1 minute. That is unacceptable, because you create a huge unbalance and other protections will trip also. But that's how you identify breaker fault. Again, is based on the current on both sides, voltage on both sides if you want, and also comparing the power poles 52 with the auxiliary 33 A or B. A in sync with 52, B in negate logic. Now what's happening if I have a breaker fault? Just to finish, I will not rely on the breaker. I will order the breaker to open, but whatever breaker does, we don't know. So we will be forced to trip all the breakers in the zone. So this is bus coupler. This is actually a switch. The same idea on the bottom. You need to have, on the top, you need to have CTs on both sides. And other situations here, bus coupler consider CT on both sides, right? So this is the normal way. Even for a bus coupler is called here, but is actually a load switch. Bus double single bus breaker, double bus single bus breaker with a transfer. We talked about this. This is the dynamic moving from across from one bus to the other. The zoning that is changing is a review of the dynamic move of the zoning that we need to analyze for protection. Paralleling operation 1 and 2 if you synchronize. So now we have to consider the settings for double bus feeder, double power, double short circuit power, for tripping and selection of the breaker. Bypass CT do not measure through current in this case, because the bypass CT, which is on the bottom, you see the current flow through the closed switch and is avoiding the switch, the CT on the bottom. So that is a wrong positioning of the CT. If you have a bypass CT, that CT should go after the bypass. So that's a problem. You need to measure the correct total current in all situations. Typical logic with bus zones. This is logic that you set in the controller for blocking or permissive of the trip. Coupled buses out of service, and the voltage induced in a bus that is out of service may happen, and you need to watch for that too. In-zone grounding of power transformers, usually solidly grounded for low voltage and high voltage, and that's from up to 1 kilovolts and above 70 kilovolts, and in between from 1 kilovolt to 70 is medium voltage, which is resistive grounding and can be high resistive with maximum 10 amps neutral to grounds on short, or low resistive with up to 1000 amps neutral to ground. There are pros and cons for each one. Out of service breaker grounded both sides, so this is the correct way to eliminate any induced voltages from other adjacent neighbors buses or backfeed. Differential connected overcurrent relay for stub bus, so you have a PT after the stub, which will confirm the open switch. Expanded bus differential zone for including the stub, so now we have the stub included with expanded zone. You see a CT on the bottom right side, is not after the first breaker, is also one after the second breaker to include the stub in the protection. And breaker failure logic, we have templates in the digital relays, and we just need to know how to use those templates, but basically they work on these assumptions, as we said, confirmation from the auxiliary contacts or confirmation of current and voltage. And these are coordination for remote and local backup. So you have local backup with delay for the primary, and then you have remote that is overlapping 20% with your zone, and those are also set up with more delay than the actual backup. So you have a backup of the backup from the adjacent zone. And that will conclude our presentation for the bus protection and zoning. Is any questions that we may have? Any questions? I don't hear any questions, so if you come up with any questions later, you are welcome to actually send me an email or to propose a topic for the next session that probably it will happen Thursday next week. Thank you very much for attending, and I wish you a nice and productive day. Let's adjourn the session. Thank you.